All right, let's dive right in. Today, we're basically scientific detectives. We're on the hunt for the secret behind one of nature's most mind-blowing feats, the incredible power of enzymes.
So, here's the mystery we're trying to solve. Enzymes are these biological catalysts that speed up chemical reactions by millions, sometimes even trillions of times. Without them, life just wouldn't be possible. But how? How in the world do they actually pull that off? That's the code we're here to crack. And the whole secret, the entire thing, hinges on this one idea, the transition state. Okay, imagine a chemical reaction is like climbing a mountain. The transition state is that split-second, super unstable moment right at the very peak. It's not what you started with, and it's not what you end up with. It's this weird in-between that lasts for less than a flicker. And for our investigation, this is the scene of the crime. To get to the bottom of this, we're going to follow the evidence, just like detectives. We'll look at some forensic data from an enzyme called chymotrypsin. We'll examine a master decoy built by chemists, see how scientists created catalytic copycats from scratch, and then, finally, we're going to put it all together to crack a 40-year-old cold case, the lysozyme mystery. Okay, our first piece of evidence. This comes straight from the lab looking at the enzyme chymotrypsin. What scientists did was pretty clever. They wanted to see what would happen if they made tiny little tweaks to the molecule the enzyme works on. That's called the substrate. So this table shows the raw data, the forensic evidence, if you will. Let's just focus on two key columns here. The one called Km, that tells us how tightly the enzyme grabs onto the substrate in the first place. And, you can see there's no really clear trend there. But then look at the Kcat column. That measures how fast the reaction actually goes. And wow, it just skyrockets as we go from substrate A to C. And when you visualize that data as overall efficiency, the trend becomes crystal clear. Those small changes to the substrate, even ones far away from where the action is, cause the enzyme's performance to go through the roof. This tells us something really profound. The enzyme isn't just grabbing the substrate, it's using those extra points of contact to stabilize something else. So here's the big takeaway from clue number 1. The enzyme's active site, it isn't a perfect lock for the substrate key. No, it's a perfect lock for the transition state key. All those extra little interactions aren't for holding the substrate tighter. They are there to lower the energy of that peak, that transition state, making the mountain so much easier to climb. But here's the problem, right? That transition state is so incredibly fleeting, we can't actually see it or study it directly. So how do you prove the theory? Well, let's move on to our next clue, where scientists got really clever and just decided to build a decoy. The thinking is, if you can't catch the real culprit, you create a perfect imposter. And that is exactly what a transition state analog is. It's a stable molecule that chemists can design to mimic the exact shape and charge of that unstable transition state. It's our master decoy. And here's a perfect example. See on the left? That's the fleeting tetrahedral transition state of a reaction. And on the right, you have a totally stable molecule called a phosphonate ester, which has been designed to look just like it. It has the same geometry, the same charge distribution. It's a perfect mimic. And here is the big payoff. These decoys, these transition state analogs, they bind to their enzymes anywhere from 100 to 1,000,000 times more tightly than the actual substrate does. Think about that. This is incredibly powerful evidence. It confirms that the enzyme's active site is truly exquisitely designed to fit that transition state. And this isn't just some abstract theory in a textbook. This whole idea of designing molecules to mimic the transition state is actually a cornerstone of modern drug design. For example, those powerful anti-HIV drugs, the protease inhibitors, they were designed using this exact strategy to create a perfect imposter that binds the viral enzyme and just shuts it down completely. All right, for our final piece of proof, we have what is, I think, a truly elegant experiment. Here, scientists didn't just study a catalyst. They built one from scratch by basically reverse engineering the whole process. The logic here is just genius. First, you build your decoy, the transition state analog. Then, you introduce this decoy to an immune system, which then creates these super specific proteins called antibodies to bind to it. So the theory goes, if an antibody is perfectly shaped to bind the transition state, well, then that antibody itself should be able to catalyze the reaction. And guess what? It totally works. These so-called catalytic antibodies, or enzymes, they can speed up reactions by thousands of times. Just think about what that means. By showing the immune system a picture of the transition state, we can essentially trick it into making a brand new catalyst. This is the ultimate confirmation that stabilizing the transition state is the real secret to an enzyme's power. Okay, so I think the case is closed on the general principle. Now let's put it all together and dive into a specific case that shows how all this works in the real world, the long-standing mystery of the enzyme lysozyme. So meet lysozyme. This is a natural antibacterial agent that you can find in things like egg whites and even your own tears. It works by breaking down the cell walls of bacteria. Now, its structure was solved way back in 1965, but exactly how it performed its chemical magic was debated by scientists for almost 4 decades. For decades, the whole debate came down to 2 competing chemical theories. The first one, called an SN1 type reaction, proposed that the substrate briefly forms this highly unstable, positively charged intermediate all on its own. The second theory, an SN2 type, suggested the enzyme itself actually forms a temporary bond with the substrate, acting as a direct partner in the whole thing. The question was, which one was it? The big breakthrough finally came in 2001. A team led by Stephen Withers designed this absolutely brilliant experiment. They created a mutant version of lysozyme and used a special artificial substrate. And the whole combination was designed to do just one thing: slow the reaction down enough so they could finally trap and see that elusive intermediate, whatever it was. And here it is, the smoking gun. Using a technique called X-ray crystallography, they were able to get the first ever direct snapshot of the intermediate. And what they saw was undeniable: a covalent bond, a direct link between the enzyme and the substrate. This was the direct evidence that just decisively tipped the scales in favor of the SN2 mechanism, solving a 40-year-old mystery. You know, this whole story just perfectly captures the spirit of science, and it's summed up beautifully in this quote from Albert Einstein. The original theory for how lysozyme worked, it stood for decades, and it was supported by a lot of good evidence. But it only took one truly insightful experiment to provide that one decisive piece of evidence that changed everything. It's just a powerful reminder that science is always a journey of discovery, and it's always open to new evidence.